In the last lesson, we talked about different ways that you can calculate stellar quantities. So, quantifying certain things about a star and using some mathematical relationships to find even more things. So, as a reminder, the things that we talked about were how do you find the distance that a star is from Earth? How do you use its brightness to find that star's luminosity, how much power it's emitting? How do you use the wavelengths of that star's light to figure out the temperature of the star? And then how do you use all of those other quantities to then figure out what the radius of that star actually is? Now, when we take all of these properties together and make those calculations about these given stars, we can find patterns within the stars in our night sky. And we find that they're not all the same, but there are certain things that are similar about them, and we can use those patterns to find even more information. So today we're going to talk about something called an HR diagram and stellar spectra. So another way that we can analyze the nature of a star. In chemistry, you might remember a big part or a big breakthrough in our understanding of the building blocks of matter was the invention of the periodic table. The periodic table just being a way to categorize and find patterns within different elements that could be used to predict elements that we didn't know existed just yet. Today, this HR diagram is basically the periodic table of stars. It's our way of categorizing stars so we can see relationships and find patterns that then allow us to know even more about other stars that we haven't yet discovered. If you take the stars and take their properties of temperature and luminosity and graph stars on a scatter plot like that, you will notice trends starting to form. One of the biggest things is you'll notice that there is most of the stars show up in this line kind of going diagonally down this graph. We call this the main sequence. Um, there are some other stars that show up, supergiants to the top right, white dwarfs to the bottom left. And you'll also notice a couple other things about this star. Colors are grouped together because color is related to temperature. That our redder stars are actually the coldest of our stars, whereas the blue or white stars are much, much hotter. And you'll notice something kind of weird about these scales. Here on the x-axis, we have temperature, but the temperature is not graphed in the way that we would typically think to graph temperature. And there's actually two weird things going on. Number one is it is actually decreasing as you go to the right. So you'll notice that the hottest temperature is on the left, the coldest temperatures are on the right. Another thing is that this is not a linear scale, it is a log scale. So here we go from 3,000 to 6,000 to 10,000 to 30,000. It is not perfect linear increments. Doesn't really affect your purposes at this point. You'll be able to read the increments, but just keep that in mind. Especially be careful about the descending temperature. On the y-axis here, you'll notice that this luminosity isn't measured in watts. We talked about luminosity in watts in the last lesson. Instead, it's been measured of solar units. We can describe that sometimes as L sub sun, the luminosity of the sun. One, in this case, being how much power our sun emits. A luminosity in this scale of 10 means it's 10 times as luminous as the sun, so 10 times the power of the sun. Um, 10 to the sixth is a million times more powerful than the sun. There's another shorthand that sometimes you'll see instead of L sun. You'll see L and then a circle with a dot in it. This is the symbol that represents sun, our sun. So that's the solar luminosity. Here's another version of that same diagram. You'll see each of these stars represented by a dot. For the record, this is not all the stars. If it was all the stars, there would be many, many more dots. But we see that as we continue adding stars to this chart, they are always following in these same patterns. So we don't need to show all of them as long as the patterns will continue. Now, I'm going to divide this into quadrants to help us kind of understand like where certain types of stars are likely to be found. In the top left-hand quadrant here, you can see that the temperature is the hottest and the luminosity is the highest. So these are very large stars because they're very luminous, and they're also very hot stars. So these are like your blue giants. Down here in the bottom left quadrant, these are very hot still, but they're very, very small. And we know that they're small because even though they're hot, they are much less luminous than our sun. So the only way that that luminosity could be so low with the temperature that they are is that they are very, very small stars. Then in the bottom right, these are still really small, but they're cold now. So we call these small cool stars. This is where we see brown dwarfs that we'll talk about. But more of our yellow stars show up here as well, our sun included in that. And then in the top right, this is another really important type of star that we're going to talk about in this unit. These are low temperature stars. And low temperature stars are typically very red, and they're also, in this case, very luminous. So if it was low temperature, but it's also emitting a lot of power, it must be a huge, huge star. We call these stars red giants. They are large, cool stars. So I'm going to take that quadrant away, and we're going to locate one very, very important star on this graph. And it's a star that happens to be right here on this one increment. So it shows up right here at luminosity of 1 solar uh, luminosity, and that is our sun. Our sun shows up right on this main sequence. If you're ever trying to find it, just look on the left-hand side, find a luminosity equal to the sun's luminosity, and figure out where that lands on the main sequence. That's where you're going to find it. So reality is our sun is a smaller, cooler star compared to the other stars that we know to exist. HR diagrams, I think, are beautiful. It's kind of a cool chart, and not a very like we're used to seeing things in grids in science, and this is not a grid. This is a graph, but it has kind of this cool scatter plot feel to it. Because of that, you'll see HR diagrams show up in art every once in a while. So here are a couple of my favorites: Twinkle Twinkle Little Star, talking about the HR diagram, and then my personal favorite, this juggler with a bunch of different juggling balls. But you'll notice that if you understand something about the HR diagram, that the top left are our blue giants, top right are our red giants. Then we got kind of the main sequence stars, with some white dwarfs kind of hidden over here. Really, really cool piece of art. So, as I mentioned, our sun is a smaller, cooler star. It's hard for us to really accept that just from what we can see here on Earth, because if you look up at the sky, you see the sun is significantly larger in our viewpoint than any of the stars. And we can't really see much color change either relative to the different things. But that is only because the sun is very, very close and the stars are much, much farther away. So it's pretty powerful to see just how big these stars can get relative to the size of our sun. In your physics data booklet, we have talked about these quantities before, these different properties of how to relate brightness and luminosity, as well as how to relate temperature and the maximum wavelength. We're going to use that here to find some other different properties that we can figure out through these HR diagrams. So let's use an HR diagram to figure out some more information about a star. If you remember back to last lesson, one of the things that we were given was a parallax angle to find the distance that the star is from Earth. And that worked great. But the problem is that only works if the star is relatively close to the Earth and is in a field of stars that is far more distant, so you can see it moving back and forth. Most stars don't fall into this category, so we need other ways that we can find distance. We're going to use an HR diagram here to see how we can use this pattern that shows up to find a distance knowing some other things on the star. If we're given that the maximum wavelength of a distant star is measured to be 600 nanometers, we can take that 600 nanometers and plug it into this equation given in the data booklet that the max wavelength times the temperature is this constant 2.9 times 10 to the negative 3. And we can find that the temperature is going to be roughly 4,800 degrees Kelvin, so just under 5,000 Kelvin. We're also given the brightness of that star. We can find its distance given that information. Now, looking at this HR diagram, we see that most stars show up on this main sequence. If it is not a main sequence star, we typically know something else about it that suggests it's a red giant or a white dwarf. So here, we can find that roughly 5,000 degrees Kelvin on the scale and trace it up until we find where that lands on the main sequence. Then, if we know that we're looking at a star roughly here, we can trace it to the left to figure out where it lands on our luminosity scale. This luminosity is given in terms of solar units, and we can see it's landing about half a solar unit, about 0.5. You don't have to be too exact here. A rough estimate is good enough. Given the luminosity of our sun to be about 3.84 times 10 to the 24th watts, we can multiply that by 0.5 to find that this particular star has a luminosity closer to 1.92 times 10 to the 24th, half that of our sun. Now, if we're given the luminosity, we know how much power this star is emitting, and we know how bright that is by the time it gets to planet Earth, we can actually figure out its distance because this relationship relates luminosity and brightness by the distance. Solving that for distance, we can find that the distance has to be the square root of luminosity divided by 4 pi times the brightness. Basically, we're multiplying both sides by 4 pi d squared, then dividing both sides by 4 pi b, and then taking the square root. I can plug the numbers that we have here into this equation. That the luminosity is 1.92 times 10 to the 24th, and the brightness that was measured is 1 times 10 to the negative 12th. Plugging that in, taking the square root, I can find that the distance is roughly 3.9 times 10 to the 17th meters. So we can do this for another star as well. And it's basically the same process that if we're given a maximum wavelength, we can find its temperature. If we know the temperature, we can find the luminosity. If we know the luminosity, we can find, or relative to the sun, we can find the luminosity of the star, plug it in, and find a distance. Finding this distance is a really, really powerful tool. Again, parallax was one way that we could find the distance that Earth is to a star, but that can only take us so far. So this is our next technique to be able to find that property of a star. Something that we're not going to get into a whole lot of detail here, but there is a relationship between mass and luminosity, that the more luminous a star is, the more massive that star is. And it's kind of an interesting relationship. The proportionality here is related by mass raised to the power of 3.5. If you do that, you'll get a nice linear relationship in this log scale. And you'll see that this property shows up in your data booklet. Like I said, not something that we're going to have to calculate uh, too much in this class, but know that the more massive a star is, that is very much related to its luminosity. So bigger, heavier stars are also putting out more power. And if they're the same distance from the Earth, they're going to be brighter in our night sky as well.